Hello. We'll talk about special matrices today. That's the last course from the series, and some matrix tricks related to Fourier matrices, discrete Fourier analysis, things like that. So these are things which are always very useful to know. You can use them all the time. So let's find this this presentation. Here we go. Special matrices and matrix tricks. So in order to get started, the Vandermonde formula, that's very interesting. You might know it, if not, here it is. So we put ones and then x1, xn, and then powers of x1, xn. We complete up to the power n minus 1. So a square matrix. So let's compute the determinant of this. And it's quite tricky. So the determinant, if you look at this, it's a polynomial, right, in x1, xn. Remember, for instance, that formula with permutations. I mean, expand, it's going to be a polynomial. And the degree is n minus 1 in each variable, because let's say x1, definitely it's n minus 1 from here. And then when I expand, I cannot multiply this with things on the same column, right? I have to multiply it with things here, which don't contain x1. So polynomial degree n minus 1. Now the point is that if you make xi is equal to j, for I different from j, the determinant will vanish because two columns will be equal, right? So this means that these are zeros of the polynomial. And finally, if you think a bit, so it should be like the product of xi minus xj, right? Times some scalar. Because this product divides the polynomial, and since you have degree n minus 1, the degree is completed somehow, so it's complete. So we only have room left for putting a scalar. Now the scalar were replaced by reference, and it's 1. So that's the formula, very useful. Now, we'll be interested in a Fourier matrix. That's a special Vandermonde matrix. So let's take the roots of unity of order n. The first one, let's call it W. And let's put the powers of W, I mean the roots of unity, in this Vandermonde matrix. So let's go back. You see 1, 1, 1, and then I put 1W, W squared, and so on, W and minus 1, and then powers of these guys. So I get this matrix here, okay? So this is best written, it's called Fourier matrix, we'll see later why. And well, I would like to say that this is omega W to the power ij, right? But in order to do this, you see the first row and columns are 1, so you have to shift indices. So that's the convention in discrete Fourier analysis. Indices always go from 0 to n minus 1 in order for this Fourier matrix to be like this in a very nice form. Now, why is this important? For several reasons. So the first thing to be known about it is that it's unitary. To be more precise, you have to rescale by square root of n. So why you just compute, you get the sum of roots of unity. And now I use the fact that if I take a root of unity, here it's w to the I minus j, and I take its powers and sum, I get a regular polygon there, okay? So that's the barycenter of a regular polygon. So it's always 0, the center of the plane, right? Unless I is j. When I is j, this polygon degenerates. It stays there at 1, and it's n, the sum. Okay, so that's the formula that we need. It's something with root of unity, but it's just the fact that the barycenter of a regular polygon is 0, unless the polygon is degenerated. So now this means that ff star is n times the identity. So if you rescale, you get a unitary. Now this matrix is very come on, cat, come here. Cat here. And the matrix here is oops. Oh, cat, say hello. So the first application is that if I take a circular matrix, circular means you just have a vector and then you start cycling it. This must be Fourier diagonal. I mean, Fourier transform, it must be diagonal. And that's very, very important for application in any problem regarding circular matrices. You have to use this. I mean, you can use this and you just solve the problem. And in addition, well, the first row vector of H is very simple. It's the Fourier of the diagonal of Q. So let's see how the proof goes. Well, just the same Fourier computation all the time. Use the fact that the sum of roots of unity is 0 unless the exponent is 0, where you get 1. So that's it. Now, more generally, so I was telling you, every time you see circular matrices, you can apply this. What happens is that not only the matrices, you see the circular matrices are those which are Fourier diagonal, but, oops, cat is gone, too complicated for him. But when you take unitary or orthogonal matrices, these things are read in Fourier in a very nice way. So the first one is something that we already know. So Q is the diagonal vector, the diagonal of capital Q. Another point is that if you take unitary matrices, this can be read in Fourier. So Q must be, all the entries must be on the unit circle. Why this? Well, it's just clear. I mean, because if you want to pass from here to here, you have to assume that matrix is unitary, which means that the eigenvalues must be on the unit circle. So here is your condition. And finally, if you want to look at orthogonal matrices, now you have to add in addition the fact that the matrix is real. And in Fourier, it's not exactly that the QIs must be real, but rather QI bar should be Q minus I for any I. So this you get it. Well, you have to once again do this Fourier transforms, whatever you get it. So very important. Every time you see circular matrices, arbitrary, unitary, orthogonal, it's better in Fourier. Now, one more thing now about bistochastic matrices. These are very interesting tools. So another application of discrete Fourier analysis using this Fourier matrix Fn. So take the groups Bn, the orthogonal matrices, which are bistochastic. I mean, sum on each row, each column is 1. And also Cn in Un, same thing. So these appear in a lot of problems. And the point is that these are actually orthogonal and unitary groups, but shifted, I mean, of dimension -1. So as this is true, the idea is that you can get this isomorphism by kind of Fourier transform. To be more precise, so stochastic, I mean, the sum on rows is 1, means exactly that if you take the one vector, let's call it psi, psi must be psi. Okay. Now, if you're in the unitary case or orthogonal, this actually implies that the rows, the sums on the columns are 1, 2. Okay, just multiply this by star, so you get you star psi x psi 2. So this is the condition for a unitary matrix to be stochastic. Now, psi, the point is that this is just the Fourier matrix applied to E0. E0 is 1, 0, 0, 0, and so on. Okay, so this can be written like this. Now is the fact that f is unitary, I multiply by f star. So f star uf must be a matrix which sends 1, 0, 0 to 1, 0, 0. So it has to be block diagonal. First you have to put 1 and then something here. Okay, so that's a condition for the matrix to be bistochastic, unitary matrix, is that in Fourier it must be block diagonal, 1 and then something else. So you're done. I mean, then that's the isomorphism. That something else must be unitary. There's no restriction on it. So you get this isomorphism 2. Now by taking real parts, let's say you get this 1, 2. Okay, so very nice. Every time you see circulant, you do it in Fourier, and also bistochastic, you do it in Fourier. Now let's take a look at these Fourier matrices. Why are they so interesting and all that? Let's try to understand. So the good framework is that of Hadamard matrices. These are generalizations of Fourier matrices. They're very interesting. So it's square matrices, all the entries are unit circle, and the rows are pairwise orthogonal. So as an example, the Fourier matrix not normalized now. I mean, just roots of unity like this. W by J. The scalar products between rows are well, the good old thing. I mean, sum of roots of unity that vary center, and it works. And the rows are pairwise orthogonal. Actually, it's something that we already know because it's unitary, right? So rows are pairwise orthogonal. Okay, so we did the computation once again, no problem. It's always good to have these computations done, even if we know them. Now, the point is that, so I was telling you, you can judge the Fourier matrices, but here I'm using a bit of advanced algebra. Well, you have to believe me. So given a finite abelian group, for those who know, you can take the group dual, I mean the characters, and then the Fourier coupling between G and G hat. I'm trying to explain why it's Fourier. But it comes from this Fourier, from a Fourier coupling. And the thing now is that, well, that's a square matrix. I mean, G and G hat have the same number of elements. They are isomorphic, and this square matrix is exactly the Fourier matrix. If you plug in a cyclic group, in general, it's a product, tensor product of such matrices, and it's Hadamard. So I have all this follows from group theory. It's a bit abstract, but it tells you that the matrices that we were calling Fourier before, it's exactly the Fourier matrix in the sense of Fourier analysis of the cyclic group Zn. And you can do it for any finite abelian group. So let's some examples which are not cyclic now. Well, we start with the cyclic group Z2. So that's the matrix, of course. I mean, remember, it was one first row, first column, and then these roots of unity. Here I just put -1. That's all. It's also called the first Walsh matrix. Now let's tensor this matrix with itself. So we'll get the Fourier matrix of the Klein group now. It's different from what we're doing before. We're no longer cyclic. So you get the second Walsh matrix. It's something like this. Enjoy, you can tensor and tensor. You get all these other matrices which are real now. That's very interesting. These are called Walsh matrices. They're useful in radio transmissions, coding, all that. Very interesting questions. So there are many questions regarding the Hadamard matrices, complex and also real. And one of one is the following one. So the size of a real Hadamard matrix, well, it can be 2, but then if it has at least 3 rows, you do some combinatorics and you see that the size must be a multiple of 4. And the big conjecture, which is more than 100-year-old, maybe 150, is that there is at least one Hadamard matrix for any multiple of 4 as size. And now, and there is no joke here, this is verified up to this number of the beast, 666, as of now, 2020. Meaning that this is not a multiple of 4, so it's true for up to 664, and it's not known starting from 668. So there's a bit of magic here. This bad number appearing, very good conjecture. Now let's end now with some continuous stuff. I mean rotations. That's something we haven't talked. Well, this was somehow discrete stuff. So this is a reminder now. So looking at unitaries, and these are things which preserve scalar product or the norm, or which satisfy U star is U minus 1. That's things that we've seen already from this formula, or which have eigenvalues on the unit circle. That's something that we know too from spectral theory. Now let's try to compute this. I mean, these are complex rotations somehow. So the first theorem is that in 2 dimensions, those of the determinant 1 are like this, AB minus B bar A bar. Would they be satisfying this? They're kind of a complex sphere. So how to prove it? Well, I just pick a matrix of determinant 1 and write that's the unitarity condition. So U star is this, right? With transpose you put bars. And U minus 1, well, it's 1 over that, but that is 1. And then there is this matrix here. I mean, you have to do this on the diagonal and put minuses here. You see, that's our equation. So, well, that's the solution, of course. And now the determinant must be 1. So A, B are subject to this. So that's a 30-second proof. And this is tricky. I mean, every time I give it to students, they can do lots of things which are complicated. That's the simplest proof. A very interesting result. And with this, we can now formulate a very nice result, Euler-Rodriguez formula. So these are the unitaries in M3 of determinant 1. I mean, the rotations in real life, okay? Whenever you do something like engineering, whatever, you need these rotations. So that's your formula. So the proof is a bit complicated. Once again, we need a bit of algebra, but let me tell you the idea. So let's go back to the formula before. So unitaries 2 by 2 determinant 1 is this. Now, if I write A is x plus iy and B is z plus it, x, y, z, t must lie on a sphere, right? So you see these matrices and these 2 by 2 unitaries of determinant 1 are of this form, with x, y, z, t satisfying this equation. They are on the sphere if you want to of space-time and for dimensional space. Okay. And now the point is that, but this is a bit tricky. This thing here somehow should appear as a kind of adjoint matrix associated to this up to plus a 1 here. Where for those who know representation here, you take the adjoint representation of U2, SU2, that's 4-dimensional. This is 1, a trivial representation, direct sum on the fundamental representation of 3. So somehow you have to square this guy and subtract a 1 in practice. That's how you get this formula here. You see, I mean, the coefficients here, somehow you square the guys here and you subtract somehow 1 because you get too many 16 instead of 9. So this is very good. Yeah, there are proofs for this. I mean, but you have to spend a bit of time in understanding of this. It's not exactly trivial. So, well, with this now, we can do a lot of things. Motional rotations, you can do engineering, also write 3D game software, right? Every time you're playing a game, and you push a button there, and your character there is, well, it's moved by a rotation like this. This formula appears in any kind of software. So very, very interesting. So hope that you like it. And in general, if you like algebra, linear algebra, there are many books, everything. And you can also check more videos here at the channel. There, everything at my channel is a continuation of all of this, this first lecture. So we have operator algebras, probability, classical and free, group theory, many things, matrix groups, quantum groups, non-commutative geometry, everything. So see you soon.